In this video, we will cover the hand layup of carbon fiber composite parts out of Prepreg material. First, we will take a look at some considerations relevant to working with Prepreg materials. We will then perform a hand layup of a flat panel part using good practices. We will then produce 5 more parts showcasing poor material deposition practices and observe the effect on part quality outcomes. After watching this video, you will be familiar with some considerations to be aware of when performing a Prepreg hand layup. What is Prepreg? Prepreg is a material consisting of fibers that have been pre-impregnated with resin. The resin is partially cured at the factory before storing and shipping at -18 degrees Celsius. Storage at low temperatures prevents the resin from further curing during storage. Resin curing progresses at room temperature, but is inhibited by low temperatures. The total cumulative amount of time that a roll of material has experienced room temperature is called its out time. Out time is typically tracked and should be minimized as much as possible. When the degree of cure becomes too high, it can be difficult to process into parts. It becomes stiff and less tacky, making it difficult to place into the tool. Prepreg must also be protected from moisture absorption, which can reduce the properties of the final part. Prepreg is typically stored in an impermeable plastic covering while it is colder than room temperature and defrosted before opening to prevent condensation. An advantage of using Prepreg materials is that a longer material deposition time is acceptable. Prepreg resin cures slowly at room temperature until it is heated in an oven or autoclave. The heated cure cycle temperature is tightly controlled to prevent under or overcuring the part and to ensure good resin saturation of the fibers. Depending on part geometry and layup procedures, some common Prepreg defects include porosity and voids, bridging and corner thinning, fiber wrinkling, and fiber waviness. In this video, we will cover the relationship between material deposition procedures and part defects. We will now take a look at the parts of our layup. Our tool will be a flat sheet of glass which we will use to produce a flat carbon panel. On the tool surface, we will apply mold release to prevent the resin from adhering to the tool. Our material is unidirectional carbon fiber Prepreg consisting of HTS40 fiber and MTM45-1 resin. After depositing our material, we will place peel ply on the laminate. This will produce a consistent surface finish good for bonding or painting while preventing consumables from adhering to the laminate. Peel ply also facilitates some evacuation of air and excess resin as it is a permeable fabric. We will place release film over the peel ply to prevent excess resin removal and to aid in removing the rest of the consumables. We will then place the breather cloth over the release film and over some additional area where we will place the inner portion of our vacuum port. Breather cloth allows air to flow out of the layup and through the vacuum port. We will now place sealant tape, also called tacky tape, around the edge of the tool. This tape creates an airtight seal between the tool and the vacuum bag. The vacuum bag gets placed over top of the layup and forms an airtight seal around the part. A hole is made for the vacuum port and a vacuum pump is connected to evacuate the air from inside the layup and produce consolidation pressure. We will now take a look at performing a hand layup of a flat panel. Prepreg resin is sensitizing and cutting composites can produce irritating fiber fragments, so gloves and a lab coat are typically worn while handling Prepreg. Next, we will cut the Prepreg to the desired shape. A knife, cutting guide, and rubber mat are common tools for this step, as are specialized composite scissors. We will then place the Prepreg in the desired spot and orientation on the tool. Alignment can be aided by laser projector systems that indicate the correct position on the tool. A roller can be used to consolidate the Prepreg layers. Rolling parallel to the fibers can reduce the chance of damaging the plies. After placing a number of layers, typically less than 5, debulking is performed. Debulking consists of placing a vacuum bag and pulling vacuum on the layup to remove air from between layers and to compress the plies against the tool closer to their final position. Debulking can reduce part defects such as bridging, wrinkling, porosity, and waviness. Parts with complex geometry may benefit from more frequent debulking than flat ones. Debulking time will depend on the application and material. It is typically 30 minutes or longer. Recommendations may be included on the material data sheet. After all plies have been placed, the vacuum bagging consumables will be installed. For this video, we will place peel ply on half of the panel to observe the surface finish it produces. Release film is placed over the entire panel. We will place a strip of tacky tape wrapped in peel ply around the edge of our laminate. This serves two purposes: one, to aid in air evacuation in the plane of the fibers, and also to act as an edge dam, preventing deformation near the edge of the layup caused by increased pressure on the upper corner of the laminate. Breather cloth is placed. The vacuum port and vacuum bag are placed. The vacuum port is installed and a leak test is performed. If leakage is present, air can be introduced into the layup and part quality can suffer. If vacuum pressure is maintained at an acceptable level, the vacuum bag is well sealed and the part is ready to place in an oven or autoclave to cure the resin matrix. An autoclave is similar to an oven but is pressurized to higher than atmospheric pressure. The extra pressure exerted on the laminate while it is curing can improve part quality and consistency versus curing in an oven at atmospheric pressure. Autoclaves, however, are more expensive to purchase and operate. Prepregs designed for vacuum-only processing, also known as out-of-autoclave processing, typically have regions of dry fiber to aid in air evacuation. Prepreg is more permeable to air in the direction of the fibers rather than through the thickness of the plies, which comes into play when placing the consumables for maximum air evacuation. For some applications, a permeable material is placed adjacent to the part under the release film to allow air to more easily flow out of the part, therefore reducing defects. After removing the part from the tool, we can see that there are no visible surface defects such as porosity, waviness, or wrinkles. A cross-section of the part shows good consolidation with no voids visible to the eye and minimal voids under the microscope. Flat panel layup, vacuum leak. We will now prepare an identical panel, but we will not debulk between layers, and we will introduce a leak in the vacuum bag. We can see that the part is not under full consolidation pressure as a result of air flowing into the bag through the leak. After removing the cured part from the tool, we can see that the fibers have not been well saturated by the resin. The lack of consolidation pressure has prevented the part from becoming fully consolidated. In a cross-sectional view, voids are visible within the laminate. If the part had been under full vacuum, entrapped air would have likely been removed from the laminate. Male L shape. Now, we will observe some other defects common to different geometries of prepreg parts. First, we will produce two parts on the outside corner of the tool. The first will be debulked partway through and the layers will be carefully positioned. A heat gun will be used to improve pliability and tack by reducing resin viscosity, and a roller will be used to ensure layers are fully pressed into place. The second part will not be debulked and the layers will be placed without using a heat gun. After curing the two parts, it is apparent that the plies that were debulked and positioned using a roller and heat gun produced a part with fewer wrinkles and more consistent thickness. Wrinkles can reduce mechanical properties considerably due to the fibers no longer being oriented in the desired direction. Female L shape. Next, we will produce two female parts on the inside corner of the tool. The first will be debulked and the plies will be positioned with the help of a heat gun and laminating tool. The second will not be debulked and no tools will be used. After curing the two parts, we can see that the plies of the debulked part are well positioned and closely follow the curvature of the tool. The plies of the second part are not well positioned and are bridged over the corner, creating voids. The bridging of the outer plies prevents the corner area from being exposed to full consolidation pressure, resulting in reduced properties and the pooling of excess resin. Conclusion. After producing a variety of parts with different geometries, we have seen a number of defects that can be caused by poor material deposition practices. Some ways to reduce these defects include performing debulking every 1 to 5 layers to reduce entrapped air and ensure the plies are closely following the tool geometry, using a heat gun to increase drapability and tack to facilitate ply placement, ensuring full vacuum is pulled on the part and that there are no leaks in the vacuum bag or tool, placing plies accurately, storing prepreg properly to prevent excessive out time or moisture absorption. If good layup practices are followed, the occurrence of many defects can be reduced and part quality can be improved.
Thanks for watching. To see more virtual labs and learn more about composite materials, make sure to subscribe to the CKN YouTube channel.